Hello, everyone. Again, welcome to Chapter 14 of our GOB Chem 51 class. The topic of Chapter 14 is organic compounds of oxygen. The contents we'll look at in this video will be organic compounds with functional groups, properties of alcohols, reactions of alcohols, ethers, properties of aldehydes and ketones. Okay, so without further ado, let's begin looking at these topics. Okay, and I just want to double check that I'm actually sharing my screen. Yes, I am. Because for some reason, I don't think I am. Hang on 1 second. Let me double check if I'm sharing the screen. Yep, sorry about that technical difficulty. Yes, okay, I think I was sharing the screen. All right, well, better to be safe than sorry. So we are going to start looking at organic compounds with functional groups. So we've already seen alkanes and alkenes, and we can in a way say that that's the canvas on which other more interesting organic chemicals are put. And those interesting bits that we can add to alkanes, we can call functional groups. Now, functional groups are the accessories of organic compounds, and you can essentially take an organic compound and split it up into the sum of different functional groups. We only look at several functional groups in GOB, but there are many, many functional groups that exist that we won't look at in GOB. So the first few functional groups that we can see examples of here at the bottom are alcohols. So we're starting to see the motif R now. So R just stands for carbon plus other things. So it's a way that an organic chemist can summarize parts of the molecule which he doesn't want you to focus on. So other things are that have a carbon, and then we have the functional group OH. So let's for now just assume that R is carbon in general, a generic carbon. We've got carbon, oxygen, hydrogen. That's an alcohol functional group. We have carbon, oxygen, carbon. That's an ether functional group. A specific example of an alcohol would be ethanol, where here R was summarizing CH3CH2. And a typical example of an ether is diethyl ether, where you can see R was summarizing CH3CH2 as well. Okay, so we've had a look at that. Okay, so let's keep going and look at the next one. Okay, we can have alkyl halides. So for example, again, we've got a carbon bonded to X, where X can be one of the 4 halogen atoms, either fluorine, chlorine, bromine, or iodine. So that would make it an alkyl halide. A thiol group is an analog of an alcohol, where the oxygen is replaced by a sulfur atom. So carbon, sulfur, hydrogen, this would be a thiol group. A specific example of an alkyl halide would be chloroethane. Oh, I should mention as well, I'll use the word alkyl halide. You might also see written haloalkane. So if you see haloalkane written, it can be used interchangeably with alkyl halide. Okay, So specific example of an alkyl halide is chloroethane. And a specific example of a thiol is ethane thiol. So as you can see, we give the name of the alkane the longest continuous chain of carbons. Here it's 2 carbons, ethane, and then we just have the word thiol at the end. Okay. So let's start to look at some of the consequences of these functional groups. So we've seen already that an alcohol has a carbon. Oh, sorry, was there a question?
No, that's all right.
Okay. We can see that an alcohol has a carbon and then an oxygen-hydrogen bond. Similar to a water molecule. So if you remember from obviously a different chapter, that a water molecule has a bent shape. So if you cast your mind back to BSEPR theory, we had, I've just told my computer to be red and it just can't do it. I hope the Zoom people are watching this. Okay. So we know that water has this bent structure. And similarly, because we've got an oxygen with 2 single bonds, anytime you have an oxygen with 2 single bonds, you'll have a similar bent structure. And likewise, as water had a net dipole, so too will anything with any oxygen with 2 single bonds will have a net dipole. So you can see in the structure below that we've got a polar bond between this methyl group and oxygen, because carbon has an electronegativity of about 2.5. Oxygen has an electronegativity of about 3.5. So the difference in electronegativity is 1.0. And we know that anything greater than 0.5 is polar. So this is definitely polar. Likewise, hydrogen is 2.1, oxygen is 3.5. That's a difference of 1.4, which is greater than 0.5. So that's polar also. You add these 2 polar bonds together, and they on average point upwards. So this net dipole is the sum of the individual bond dipoles. So we know that alcohols, for this reason, have a net dipole and tend to be, if they're small like this is methanol, they tend to be polar molecules overall. What does that mean? That means they're probably going to be a liquid because they'll have strong intermolecular forces. They'll have hydrogen bonding because they have a hydrogen bond capable hydrogen. They'll have dipole-dipole forces, and obviously they'll have London dispersion forces because every molecule does. So these molecules will tend to be liquids even when they're small, like methane. They'll also tend to have relatively high physical properties, much higher than, for example, methane would have. So methane is a gas. So it's the same as methanol, but it lacks the oxygen. So that addition of that oxygen changes everything. So we can fine tune, a chemist can fine tune the ingredients by adding elements, and therefore can fine tune the flavor of the molecule produced. Lots of dangerous analogies there. Okay, so now we've introduced alcohols. Let's get in the weeds a bit. There are flavors of alcohol. There are 3 flavors. There's primary, secondary, and tertiary. We represent primary alcohols as a 1 degree. We represent secondary as a 2 degree, and tertiary as a 3 degree. It's important that we can identify what type of alcohol we have because they have different chemistries. And this is going to be important to us later on. In this course, it'll be next week when we look at some biochemistry implications of what we've done so far. So let's start to learn some of the basic analysis skills now, ready for next week. So a primary alcohol, you look at the carbon that contains the OH bond, which is highlighted in this tan color here. A primary alcohol's carbon is bonded to only one of the carbon. So this carbon indicated in red is only one of them. That makes this carbon a primary alcohol. This carbon is bonded to two other carbons, here highlighted in red again. So this means that this carbon, the alcoholic carbon, is a secondary alcohol. Finally, you can have three carbons, making this a tertiary alcohol. Clearly, we've exhausted the list because you can only have 4 bonds around carbon, and the fourth spot is occupied by the alcohol group itself. So the maximum carbons you can have on the alcoholic carbon is 3. So you have 1, 2, and 3, or primary, secondary, and tertiary. Okay, so in terms of intermolecular forces, again, alcohols tend to have much more impressive physical properties compared to alkanes because of the oxygen. So they can interact via hydrogen bonds, as shown by this dashed line here. So remember, a hydrogen bond is between a hydrogen that itself is bonded directly to one of 3 elements, either an oxygen, a nitrogen, or a fluorine. So for example, these hydrogens on carbon are not capable of hydrogen bonding. Only this one hydrogen on oxygen is capable of hydrogen bonding. What can a hydrogen bond to? It can hydrogen bond to one of the same 3 elements, either oxygen, nitrogen, or fluorine. So here you see a hydrogen, this white sphere here. It's bonded directly to this red oxygen, and it's hydrogen bonding through space to an adjacent oxygen on an adjacent molecule. So if you want to boil this material, you've got to break those sticky interactions. If we compare butane with 1 propanol, so butane is 4 carbons long. How does that compare with propanol, 1 propanol? Well, 1 propanol only has 3 carbons, but it's got a 4th non-hydrogen element, namely oxygen. So it's similar in molecular weight. So that's why they've compared butane with 1 propanol rather than with 1 butanol, because 1 butanol would be much heavier and it wouldn't be a fair comparison. So you can think of this as we've got 4 major atoms. They happen to be carbon. We've got 4 major atoms. They happen to be 3 carbons and 1 oxygen. And we can see clearly the more impressive boiling point. Well, both variables are more impressive, but it's dramatically more impressive, the boiling point. So again, just by swapping out 1 carbon and replacing it with an oxygen, we ramped up by almost 100 degrees. The boiling point, it's solely due to these hydrogen bonds. This alcohol can hydrogen bond, this alkane cannot. Alcohols are soluble in organic solvents. So for the pretty much 100% of the time in GOB, we are only interested in water as a solvent. But if you had an organic solvent, would just be any organic compound that was in its liquid phase, you could then add more organic chemicals to that. So you can add alcohols to that. There's a cutoff though, because if you recall what an alcohol looks like, it's got this polar hydroxyl group, but it's also got this non-polar alkane group or alkyl group. So there's like a conflict between the OH that likes water and the CHs that like other CHs, or they don't like water. So at what point does the carbon win against the oxygen? Well, roughly a cutoff is greater than 6 carbons. So there comes a point where if you have a balance between the carbon end, the hydrophobic end, or the water-fearing end, and the hydrophilic, water-loving end, it will dissolve in water. But as it gets larger and larger on the alkane side, eventually there's just too many carbons. It's just dominated by its hydrophobic nature, and the whole thing will be insoluble, despite having a polar group over here. Okay, let's look at alcohol nomenclature. So here, similar to alkanes, we want to identify the longest continuous carbon chain, which here, so we're looking at this test molecule here. They've identified the longest continuous carbon chain here in tan, and we can see that it has 6 carbons in total in its chain. Next, the big new shiny object is the hydroxyl group. We want to number either left to right or right to left this longest chain to give the alcohol the lowest possible number. So if you look at this, we can, we've always got 2 options, left to right or right to left. And literally, if you're not sure, look at both. So we've got 1, if I'm counting right to left, I've got 1, 2, 3, 4, 5, 6. If I'm counting left to right, I just reverse it. 1, 2, 3, 4, 5, 6. So we can now see the alcohol, depending on how I count, is either on carbon 3 or 4. So 4 is higher than 3, so 4 loses. 3 is lower than 4, so 3 wins. So I now know I'm going to count these carbons right to left, just because it gives me the lowest possible number for the alcohol, which is now the dominant group. So we know it's based on 3-hexanol. So again, we count right to left because it gives the alcohol the lowest possible number on the carbon chain. Hexane is because it's got 6 carbons. It's based on hexane. And the ol is in position 3 because it's an alcohol. With respect to position 3, the methyl group is on carbon 5. So the final answer is 5-methyl 3-hexanol. We can have a cyclic alcohol. So this previous example was a linear or acyclic. So we would say this is linear or acyclic. So either linear or which is equal to acyclic. So we've looked at nomenclature for linear or acyclic alcohols. We can also look at cyclic alcohols. And the naming convention is similar to what we've seen before. We prioritize the lowest number for the alcohol. So by definition, we just call that carbon 1. And because it's carbon 1, it's assumed it's carbon 1. We don't have to spell out it's carbon 1. It's just taken to be a given fact. So we have cyclohexanol because we have a 6-membered ring. And by definition, the alcohol is on carbon 1. With respect to it, we want to count either clockwise or counterclockwise to give the lowest possible numbers for the other substituents. Clearly, starting from carbon 1, I hit this methyl group if I go counterclockwise rather than clockwise, so it would be 3-methyl cyclohexanol in this case. Here we have a cyclopentanol 5-membered ring. Again, this time going clockwise, we're going to hit this ethyl group. So we'd count clockwise in this occasion, and it would be 2-ethyl cyclopentanol. What we've seen so far is the IUPAC, the International Unit of Purified, International Union of Pure and Applied Chemistry, which is the governing body that decided in the 90s that they were going to standardize the names. Having said that, there is still old, more antiquated names in textbooks, online, in the brains of old professors in old universities. that will slowly become obsolete as people retire and books get rewritten. And students that learned the IUPAC names become professors themselves and write their own textbooks. So it's a generational thing, but for now, you will still see names like methyl alcohol and ethyl alcohol. So this would be known as a common name or an older name. So we would call this 1-propanol because it's propane and the alcohol is on carbon 1. But an older person, and I say that with lots of respect, as an old person myself, might call this propyl alcohol. So if you see anything like this, you just know how to interpret it. I've got 3 carbons with an alcohol stuck on the end. Okay, that would, in these lectures, be called the common name. We can have systems with 2 alcohols. So we call these diols because there are 2 of them. So if you have a structure like this, an ethane backbone with an alcohol at either end. So by definition, one carbon is carbon 1, the other one therefore must be carbon 2. Rather than saying 1,2-diol ethane, we say 1,2-ethane diol. So we have 2 alcohols on carbon 1 and 2 of an ethane backbone. So that's an acyclic example. Looking now at a cyclic example, we have 1,2-cyclopentane diol. Clearly, it's a cyclopentane. It's got 2 alcohols. By definition, one of them is carbon 1, and we hit the other one as quick as we can, which in this case means carbon 2. So hence the name 1,2-cyclopentane diol. We saw in the alkane video, in a previous video where we looked at unsaturated hydrocarbons, that we can have part of the chemistry of alkanes was addition. So we can have hydration. Here we're going in the reverse order. We have dehydration. So whereas hydration was the addition of water to a double bond, here we can have the removal of water to create a double bond. So it's literally the opposite of hydration. So you can see here we've got 1 carbon with a hydrogen, an adjacent carbon with an OH. So clearly this is an alcohol, and you can see the tanned region has HOH. This is going to be the origin of H2O. So we're going to dehydrate this water molecule. And what's left, remember, each carbon must form 4 bonds. So if I've lost bonds to these 2 groups, I must form a bond to my neighboring carbon. So we preserve the 4 bond stature of carbon. We just have 2 singles and a double rather than 4 singles. So in general, this is an elimination. So again, previously we've seen hydration, which is an addition. The opposite of an addition is an elimination, and this specific example is a dehydration. So again, to link this back with what we've seen before, we saw hydration and we inspected Markovnikov's rule. Now we're looking at things like dehydration or elimination. We have something called Zaitsev's rule. So let's look at an example of Zaitsev rule. So we have this alcohol. It's 2-butanol. We have 4 carbons in the longest continuous carbon chain. We count the carbon chain 1 through 4, and we want the alcohol, which is right here, to have the lowest number. So clearly, going from left to right, it would be on carbon 2, so 2-butanol. We're now going to do a dehydration. So in red or pink, whatever color that is, pink, we have an H and an adjacent OH that we can eliminate to form this product, 1-butene. So we'd have the double bond here. Or highlighted in blue, we've got another OH and an H option, and we would therefore form the bond between carbons 2 and 3. So we've got two possibilities. Do we lose the red water or the blue water? Well, we try the experiment and we observe that exclusively we form 2-butene, which is this structure here. This is the Zaitsev's product. It's followed Zaitsev's rule. So Zaitsev's rule says that you basically want the double bond to form between the longest alkyl groups possible. So let's have a look at that. I think we dig into it on the next slide. Oh, no, we don't. Okay, I think we can look at an example here. I have other videos on the channel that you can look at in addition to this. So why don't we form option 1? Well, let's look at option 1. So the carbon here has 2 H's, so it has no alkyl groups, has no carbon groups. Whereas we compare carbon 1 here, if we compare the first carbon double bond carbon in option 2, it has an H, but now it has a carbon. So it's got 1 alkyl group on this carbon. Let's remember those. So here we've got 1 alkyl group. Likewise, here we've got 1 alkyl group. So this is an alkyl. This is an alkyl. Either side of the double bond. Here we have an alkyl, but here we have 0 alkyl. So it's either you have 0 and 1 alkyl or 1 total, or you have 1 and 1 alkyl or 2 total, and we want to maximize that number. If they both had 2, we would look for the longer chain. We'd look for any difference we could. And if we come up with examples that are that close, we'll look at examples. And obviously, if the molecule is symmetric, we won't notice a Zaitsev product because the product that's formed will be identical in either case. So anyway, that's the Zaitsev rule. An important thing to note, and I think I explore this further in the other video on the playlist, is that although, so maybe I can just annotate this real quick here. Yeah, so we can go from an alkane to an alkene. And actually, in this example, I don't want to say alkene, right? I want to say alkyne. Right. So in this specific example, we're going from an alcohol. We're doing an elimination to give an alkene, and we follow Zaitsev. You can then undo that and go from an alkene back to an alcohol. This would be addition. And here we follow Markovnikov. But you don't necessarily get the same alcohol back again. So this is not to be thought of as a cycle. The alcohol you start with, if you eliminate it to form an alkene and then try to rehydrate it again, you won't necessarily get the same alcohol. You might get a different alcohol. So this is not necessarily a reversible process. That's a key point, I think. Okay. So we can dehydrate alcohols. Another type of chemistry we can do on alcohols is oxidation. So oxidation to an organic chemist means adding oxygen and or removing hydrogen. So let's see this in action. So we've got our alcohol here. The square brackets with an O in just means add an atom. However, the mechanism doesn't matter, but on average, we are adding an oxygen atom. We're oxidizing it. And you can see that this oxygen atom is going to combine with these two red hydrogens to become water. So I can add water here. Those are two hydrogens, our oxygen. And then you can see what's left if we eliminate those two hydrogens. We're left with something, if we rearrange the electrons afterwards, we have a carbon, an oxygen, and two methyl groups. So we've taken an alcohol, we've oxidized it to form, in this case, a ketone. So we have a ketone. So a ketone is a functional group with a carbon double bond oxygen. So if ever you see a carbon double bond oxygen, we'll call this a carbonyl. It's a carbonyl group. Ketones have one, other functional groups have them as well. This is a ketone because a ketone not only has a carbonyl, but specifically has adjacent carbons as well. So that's when it becomes a ketone. What type of alcohol do we have here? Well, the carbon that contains the OH is bonded to two other carbons. So this is a second degree or a secondary alcohol. Secondary alcohols produce ketones upon oxidation. That's going to be useful later in the course. And it will certainly be useful in any biochemistry classes that you take after GOB Chapter. Okay, so just in secondary alcohols. Secondary alcohols can be oxidized to ketones, and that's it. Primary alcohols have more extensive chemistry. So this is ethanol, it's a primary alcohol, because the carbon containing the hydroxyl is bonded to one other carbon. We oxidize it not to a ketone this time, but to an aldehyde. So you can see that when we've lost the, when we've added the hydrogen and lost the water, we're left with a carbon, a methyl, an oxygen, and a hydrogen. So we're just gonna, there's no other carbon here. So we formed an aldehyde. Aldehydes have, get that red pen back. Aldehydes have carbonyls, a carbon, but distinctively they have an H. We can abbreviate the functional group as RCHO, where R can be any carbon structure, so RCHO. Aldehydes are more reactive than ketones, so they can be further oxidized to give carboxylic acids. Carboxylic acids take on another oxygen, so we essentially insert an oxygen between the carbon and hydrogen bond. You can monitor the progression of an alcohol's oxidation to a carboxylic acid by looking at reduction in pH, for example. So you could monitor the drop in pH as we generate this acid. Okay. So again, primary alcohols are oxidized to aldehydes, then eventually carboxylic acids. Secondary alcohols are oxidized to ketones. Okay, as we've seen already, but this slide just repeats it again. Again, secondary alcohols are oxidized to ketones, and then that's it. We've got no way to generate a carboxylic acid. Ketones are just not receptive to further oxidation. Tertiary alcohols don't undergo oxidation at all. So again, we said earlier The importance of identifying types of alcohol is because they have different chemistries. We can clearly see they do. And if we know what type of alcohol we have, we'll try the chemistry that they're capable of, and we won't waste our time trying chemistry they're not capable of. You know, if you know you have an elephant, there's no point paying for flying lessons because elephants can't fly unless it's done by them. I'm not going to do that. Okay, ethers. Ethers, we said, are oxygens with 2 single bonds to other carbons. The R groups can be the same, as in diethyl ether. The R groups can be different, as in ethyl methyl ether. Similar to alcohols, because we have an oxygen with 2 single bonds, we have this bent structure. What's different about ethers, though, they'll have raised physical properties compared to an alkane, for example, because of the presence of the oxygen, but they have no hydrogen directly bonded to the oxygen, so there's no hydrogen bonding. So they do have dipole-dipole forces, which will raise the physical properties, but they'll be lower than the physical properties of alcohol. But certainly greater than the physical properties of an alkene. We can have acyclic ethers. We can also have cyclic ethers. Cyclic ethers are relabeled epoxides. So here's an example of a cyclic ether. Again, relabeled epoxide. Epoxides are reactive because the ring here is strained. We saw on the previous slide that the typical bond angle, the stable bond angle is in a bent structure is about 109.5 approximately. We know from our geometry classes that the internal angle of a triangle is 60 degrees. So we've gone from a preference of 109 down to 60. Well, that's just going to spring open. So these are reactive ethers, prone to being sprung open. This just summarizes what I believe we've just said about some physical properties. Definitely stronger intermolecular forces than alkanes due to the oxygen atom present. Definitely weaker than alcohols due to the lack of hydrogen bonding because there's no hydrogen directly bonded to the oxygen. It's only carbon directly bonded to the oxygen. Similar shape to water because of that bent structure, the single bonds around oxygen. So they would definitely have dipole-dipole forces, and that will raise the physical properties. Let's compare. This is a nice comparison of similar comparative structures. So butane, there's 4 main elements in a row. Here they're all carbon. Ethyl methyl ether, we have 4 main elements in a row. One of them is an oxygen. And 1 propanol, 4 main elements in a row. Again, one of them is oxygen. You can see that only London dispersion forces in butane, very low boiling point. The addition of dipole-dipole forces in ethyl methyl ether, we've raised significantly the boiling point. It's still pretty low. It's a lot higher than butane, but we've dramatically increased the boiling point of 1 propanol because of hydrogen bonding. Something worth noting here, there's a relationship between ethyl methyl ether and 1 propanol. We notice they both have 3 carbons. Let me get my pen. We notice they both have 1, 2, 3 carbons, 1, 2, 3 carbons. So C3, and then 3, 4, 5, 8 hydrogens, and then an oxygen. This has 3, 4, 5, C3, 8, HO. So these are related as constitutional isomers. So these are the Mr. Potato Head isomers. Again, so don't think isomers have to be the same functional group, like they all have to be alcohols. No, they just have to have the same stuff, but be like rearranged, chemically rearranged, the ingredients that you're given. So here we've gone from an ether to an alcohol, so they would be constitutional isomers. Okay, this diagram just shows you so be careful here. So I made a statement that can be misinterpreted. I said that ethers can't hydrogen bond. So I meant they can't hydrogen bond with themselves because they don't have a hydrogen directly bonded to the oxygen. They only have carbons. They can hydrogen bond with something that is capable of hydrogen bonding. So again, this can be interpreted the wrong way if you're not careful. So we said up here, let me get my spotlight button. We said up here that ethers have substantially lower physical properties than alcohols because alcohols can hydrogen bond. With themselves was implied. Ethers can't hydrogen bond with themselves is implied. But if you add an ether to water, water does have a hydrogen that's bonded to an oxygen. So this is a hydrogen capable of hydrogen bonding. It just needs an oxygen, fluorine, or nitrogen to hydrogen bond with. So it can find that in an ether. But now we're not looking at the physical property of the ether, we're looking at a solution of an ether. So that's something totally different. We've now contaminated the ether with water, and we're no longer looking at the physical property of the ether. We're looking at this dirty mixture of an ether and water. Okay, so hopefully that's clear and you don't get confused with the presence or the absence of hydrogen bonding. Because they're two different scenarios. Let's look at the nomenclature of ethers. Again, there's a simple way or a common way to name them, and then there's the IUPAC way. So here's the simple way to name them. You look at the oxygen in the middle, and then you look at the two alkyl groups either side. So here we have a 1-carbon methyl group, and we have a 2-carbon ethyl group. We know it's an ether, so we can write the word ether. And then we alphabetize the two alkyl groups, E before M. So it's ethyl, methyl, ether, 3 separate words. If we have two identical ethyl groups, we can just say diethyl ether. So again, this is the common name or the simple name. Yeah, I'll go ahead. So the next slide is going to give you the more IUPAC or complex name, but I'll go ahead and add them here just to give us extra examples. If we wanted to give this the complex name or the IUPAC name, we would look at the longest chain, which here is ethyl. So it would be ethane, double check, I don't have any brain fog. Ethanoate, that sounds right. Let me double check before I tell all my students the wrong thing. No, I was getting confused with something else. All right, but now I caught it before I confused my other thoughts. I was getting confused with esters for a minute there. Sorry about that. All right. So we know that, now I've lost the slide. I'm sorry. Let me go back to the right slide. Okay. So we know that out of the two alkyl groups, ethyl is the longest one. So we'll say that's an ethane backbone. All right. And then we lump the oxygen with the shorter group, and we make this an alkoxy group. X. So it's an alkoxy group. If the alkyl part is methyl, it's a methoxy. So this would be a methoxy group. The one on the right would be an ethoxy group. So it would be methoxy methoxyethane. This would be ethoxyethane. It should be all one word. I believe methoxyethane, methoxyethane. Okay, again, so we've just seen methoxy and ethoxy. So we can see more examples here. Again, we know it's an ether because we've got this carbon, oxygen, carbon motif. We identified the longest continuous chain here highlighted in tan. And then we've got this ethoxy group that's the shorter of the two alkyl chains. So the longest continuous chain contains 8 carbons. So it's an octane. And then we've got this short ethoxy group. So the name is 4-ethoxy-octane. So this is the IUPAC way to name it. But again, we have the simple way. So if I now write the simple name, and again, you'll see both. If we wrote the simple name, we've got 2 carbons. So that would be ethyl. And then this would just be 8 carbons. So actually, I'm going to halt right there. You wouldn't actually use the simple name. Why? Because you could use the simple name if it was bonded on the end, but notice it's bonded in the middle, or it's bonded on a carbon, not on the end. If it were bonded on the end, we could say ethyl, octyl, ether. However, we can't in this case because it's not bonded on the end, it's bonded on the middle. So we would not bother with, there is no simple name here, we'd have to go with the IUPAC name. Okay. Just a couple more slides. Again, I think we've talked about what's on that slide. If I just duplicated the same thing twice, no, I just don't think I moved the slide. Okay, so I was on this slide. That was the, okay. So then this slide, aldehydes and ketones. We've already introduced them. We've mentioned that, again, something I never mentioned. So let's just draw an aldehyde again. We never mentioned what types of forces aldehydes can make. And I guess we didn't because it's right here. Remember, an aldehyde has a carbonyl, a carbon, and a hydrogen. Aldehydes cannot hydrogen bond because the hydrogen is not bonded to oxygen, it's bonded to carbon. So there is no hydrogen bonding with aldehydes with themselves. It can hydrogen bond to water because water has a hydrogen that is bonded to oxygen. So you can form a hydrogen bond like that, but it can't hydrogen bond with itself. So when we look at physical properties, we're not looking at water, anything. We're looking at the aldehyde bonding with itself, and it can't hydrogen bond with itself. So whereas it does have dipole-dipole forces because of the carbonyl, it doesn't have the extreme dipole-dipole forces that it would have if it could hydrogen bond. I'm not focused on nomenclature of aldehydes in this GOB course. Some GOB courses do more heavily look at nomenclature of everything. But you can always tell an aldehyde because it ends with the two letters Al. So butanal is an aldehyde with 4 carbons. Hexanal is an aldehyde with 6 carbons. So it always ends in Al if you have an aldehyde. Okay, penultimate slide. Ketones likewise can form dipole-dipole forces, but they cannot form hydrogen bonds, again, because the carbonyl is not directly bonded. It doesn't directly have a hydrogen bonded to the oxygen. So no hydrogen bonding. So as you can see, the ketone and ketones end in the 3 letters O-N-E, one for ketone. So 2-butanone, essentially, again, I'm not really bothered about the name of ketones in my particular GOB class, but they're pretty self-explanatory once you've been introduced to a little bit of nomenclature. So again, I want to look at the longest continuous chain of carbons. Here it's 4. It's a ketone, so butanone. And I have to tell you where the carbonyl is. Well, the carbonyl, I want to give it the lowest possible number. So here, the lowest possible number I can give it is 2. So it's 2-butanone. The 2 tells you the location of the carbonyl on the carbon backbone. Okay, so 2-butanone has lower physical properties than 1-butanol because the alcohol can hydrogen bond, the ketone cannot. And again, these are constitutional isomers of each other. Even though they're different functional groups, they have the same type and number of constituents. Okay, and the last slide is, again, the solubility of these things. So again, we've got the carbonyl. It can form hydrogen bonds with water. That means it has the potential to be water soluble if and only if we don't have too many carbons either side. And this applies for ketones or aldehydes. Similar to what we said about alcohols, how many carbons is too many? It tends to be around 6. So if you have aldehydes or ketones with fewer than 6 carbons total, there's a good chance it will be water soluble. More than 6 carbons total per oxygen, there's a good chance it won't be. So roughly for every oxygen, you need for every 6 carbons or less, you need at least 1 oxygen. So if you have a diol with 2 oxygens, you can have up to 12 carbons and you might still be soluble. Okay, so that is going to conclude this video. So I will see you in the next video.